Hello and welcome to this class. My name is Kirsten Mubani and I'm here to teach you chemistry. The theme of our class is the chemical world and our topic is symbols, formulae and equations, part 2. At the end of this class, you are going to know the laws of chemical combinations and you are also going to know how to write chemical equations. Now, when it comes to how elements combine with themselves and with other elements in a chemical reaction, there are some laws that govern this action, okay? Those laws are known as the laws of chemical combination. They are law of conservation of mass, law of constant composition or definite proportion, law of multiple proportions, and the law of reciprocal proportions. But for the sake of our class, we'll be treating the first 3 laws of chemical combination. Now, the law of conservation of matter. This law states that matter can neither be created nor destroyed. Rather, it can change from one form to another. Now, this means that when elements combine to react, okay? No new substances or elements are formed in the course of any chemical reaction. The same elements that start the reaction would also be the same elements that will be produced in the product. The first one is the law of conservation of matter. This law states that matter can neither be created nor destroyed, but can change from one form to another. Okay, so it's trying to tell us that when elements are in a reaction or they are combining together, okay, to form something else, no new substance is formed at the end of their reaction. For example, if we have carbon reacting with oxygen to form carbon monoxide, this reaction, it's the same carbon and oxygen that started the reaction that will be present in the products. And they will also be present in the same numbers. They will not change. If a new substance is formed, it means the product will have maybe nitrogen coming in, or magnesium, or any other element. But you can see that when they react, no other elements can be formed in their product. And we say that the total mass of reactants is always equal to the total mass of products formed. Think about it. If the elements do not change, if they are still there in the same number, it means that their weight will remain the same, and so their mass will remain the same. So the mass of these reactants, when calculated, would equal the mass of these products when calculated. So we have an example here. We have one methane molecule combining with 2 oxygen atoms to form carbon dioxide and water. You see that there is a change from one form to another. The methane and oxygen molecules combine to form carbon dioxide and water. So there's been a change of form, no doubt. But if we calculate the number of the elements or the atoms, okay, that took part in this reaction, if we calculate that of the reactants and that of the products, we'll realize that there was no change. They remained the same. You can see methane here has 1 carbon atom and 4 hydrogen atoms. And here we have 4 atoms of oxygen. They reacted to form carbon dioxide and water. Carbon dioxide is made up of 1 carbon atom and 2 oxygen atoms, while 2 molecules of water we have 4 hydrogen atoms and 2 oxygen atoms. You can see that there was no change. If we count, we'll see that this 1 carbon atom remains 1 carbon atom. In the reactant, no other carbon atom was formed. 4 hydrogen atoms, we still had 4 hydrogen atoms in the products. 4 oxygen atoms, we still have 4 oxygen atoms in the products. We have 2 here and 2 here. So we see that there was no addition, there was no subtraction, same number of atoms that started the reaction, we have the same number of atoms that were present for the products formed. We can also see that when water decomposes into the component elements, okay, we have 2 molecules of water here, one here and one here. So we have 1, 2, 3, 4 atoms of hydrogen and 1, 2 atoms of oxygen. When it decomposes, we still have 1, 2, 3, 4 hydrogen atoms and 2 oxygen atoms. So the law of conservation of matter is telling us that matter cannot be created. If it was created, then we would have had additional elements, right? It can also be destroyed. If it was destroyed, we would have seen maybe less of these atoms in this equation. Let's have a quick exercise to further illustrate this law of conservation of matter. Let's say you kept an iron rod in your backyard and forgot about it. Over time, you remember it and you go for it, but you see that it contains some rust. Now, before this time, you had taken the weight or mass of this iron rod to be 178 grams. And after the rust, you weighed the iron rod again and you realized that it's now weighing 197 grams. So the question is, what is the mass of the oxygen that reacted with the iron to form the rust? Which means something would have reacted with the iron, and that is oxygen. So to buttress this law of conservation of matter, we are going to find the mass of the oxygen that reacted with this iron rod. And so at the end of the day, we'll see that what we have for the reactants is also going to equal what we have for the product. So before rust and after rust, and before rust we had the mass of the iron rod at 178 grams, and after the rust we had it at 197 grams. Putting it in the form of an equation, we have these 2 atoms of iron reacting with oxygen to give us iron oxide. So for us to find the mass of oxygen that reacted, we said mass of iron plus mass of oxygen equaling mass of rust. Therefore, mass of oxygen alone will be mass of the rust minus the mass of the iron rod. So mass of the rust was given to us as 197, and mass of the iron was given as 178. So if we subtract this, we'd have 19 grams. Now, if you add this 19 grams to the 178 we had initially, we would get 197 grams. So you see that before the reaction and after the reaction, that the masses are the same. So this goes to prove the law of conservation of matter, that matter is not created or destroyed. Now we have the law of constant composition, or otherwise known as the law of definite proportion. It states that all pure samples of a chemical compound always contain the same elements combined in the same mass proportion or size. For us to be able to understand this better, we have something on the board to illustrate the law of constant composition. And we are going to be making use of water to illustrate this law. So it says that all pure samples of a chemical compound contain the same elements combined in the same mass proportion. We have water, and it's composed of hydrogen and oxygen. So element 1 is hydrogen, and element 2 is oxygen. But for water, we have 2 atoms of hydrogen, so we'd have H2, okay, and just 1 for oxygen. Now, their mass proportion would be hydrogen has a molar mass of 1, and since it is 2 here, we'll have 2 for hydrogen. For oxygen, it has a molar mass of 16. So it means that the ratio of hydrogen to oxygen is 2:16. And when we factorize out, we'll have 1:8. Now, this law is telling us that for every pure sample of water, okay, the ratio of hydrogen to oxygen would always be in this form of 1:8. So it doesn't matter if it's just a drop of water, or if it's a cup of water, or if it's even an ocean of water. So long as it is pure water, the ratio of hydrogen to oxygen would always be in 1:8. Other examples we have, let's say ammonia. This is ammonia, okay? And here we have 1 atom of nitrogen combining with 3 atoms of hydrogen. So anywhere you have a pure sample of ammonia, whether it's in your cleaning agents or in anywhere ammonia is present, it's going to be present in this ratio. If this ratio were to change, it will no longer be ammonia, but something else. Likewise for water, if this ratio were to change, it will no longer be water. It will now be another element. So this is what this law of constant composition tries to tell us, that for every pure sample of a chemical compound, it will contain the same elements, okay? As you can see, for water, we'll always have hydrogen and oxygen. It will never be nitrogen or carbon with oxygen. It will always be hydrogen and oxygen. So it has the same elements combined in the same mass proportion. As you can see, they have definite mass proportion that can never change. So we say that the law explains that the elements that form a compound are identical in composition by mass. The elements are always identical. For water, it's always hydrogen and oxygen, as we earlier said. And then it also shows that the mass of the two compounds are always in definite proportion. As we also saw, water is always in that proportion of 1 atom of hydrogen to 8 atoms of oxygen. So this is basically about the law of constant composition. Going over to the law of multiple proportion. This law states that when 2 elements, A and B, combine together to form more than one compound, the mass of element B, which combines with a fixed mass of element A, does so in simple whole number ratios. Now, this law may sound kind of ambiguous, but if you take it step by step, it says if 2 elements, so we have one element A and another element B. So let's use A, B to represent 2 elements. Form more than one compound. It means that these elements can form elements AB, AB2, AB3. Remember, it's those same elements that are forming more than one compound. So you can't have A, B, C. It will still be the same elements forming more than one compound. Then the ratio of the masses, or mass ratio, of the second element, which is B, which combines with a fixed mass of the first element, which is A, will be ratios of small whole numbers. Okay? For example, using compounds formed from nitrogen and oxygen. So these are our elements, A and B. We have nitrogen and oxygen. Okay? They are forming more than one element. We have this, and this. Okay? So, in calculating or trying to prove this law, we have a simple method we follow. Remember that they are in form of ratio, and so we like to put them in this form. So it can also be written in this form, okay? And so the best way to put it would be N2 over O for N2O. So we have it written in this way, same for nitrogen oxide and nitrogen dioxide. Then the next thing, we make use of their mass numbers. And the mass number for nitrogen is 14. The mass number for oxygen is 16. So here we have 2 atoms of nitrogen. So it's going to be 14 times 2 to give us 28 over 16. Here we just have 1 atom of nitrogen. So we have 14 divided 16. And here we have 14 over, we have 2 atoms of oxygen here. So we have 16 times 2, which is 32. So we have 14 divided 32. Then when you calculate that, you are going to be having 1.75 for the first compound, 0.875 for the second compound, and 0.4375 for the third compound. Now, you can see these arrows pointing down together. If you pick the first two compounds, okay, and divide by the smallest number, you're going to have a simple number, which is 2. If you also pick the next two compounds and divide by the smallest number, you're going to have 2 as your answer. So you see that in comparing these compounds, you can see that these numbers, okay, are indicating that they are present in simple whole number ratios. This is what these numbers are indicating. So you see that they are just simple numbers. They are not even more than 2 or 3. Just simple whole numbers. So that is what this law is trying to prove. But remember, it's talking about compounds of the same elements. Okay? Here as well, we have carbon and oxygen forming carbon monoxide and carbon dioxide. If we go through the same process, we'll see that carbon monoxide and carbon dioxide are present in simple whole number ratios. And as I said, it's compounds composed of the same elements that have this feature. So we say that the law only applies to compounds composed of the same elements, such as carbon and oxygen. You can see some compounds formed from 2 elements. We have carbon monoxide and carbon dioxide formed from carbon and oxygen, and other compounds we have here. Now, chemical equations. From our previous class on symbols and equations, we talked about how symbols are used to represent elements, compounds. So going further, we have what we call chemical equation. It's a way of representing chemical reactions with symbols and formula. For instance, if you have sodium reacting with iron chloride, we are not going to start writing out sodium in full or iron chloride in full. We make use of symbols of these elements to show their reaction. From this, anybody can look at it and understand that sodium reacted with iron chloride to form sodium chloride and iron. So this representation is what we call a chemical equation. So there are some information that we get to have when we write chemical equation. 1, chemical equations tell us the states of the reactants and the products. Okay? It tells us if they are reacting in their solid forms, their liquid forms, gaseous forms, or aqueous forms. So S is used to represent reactions in their solid form. L is for reactions in liquid form. AQ is for reactions in aqueous form, while G goes for reactions in gaseous form. So for example, we see hydrogen chloride is reacting in its aqueous form with calcium carbonate in its solid form to give calcium chloride in aqueous form, water in the liquid form, and carbon dioxide in gaseous form. 2, it tells us, chemical equations tell us the nature of the reaction. It tells us if the reaction is a reversible reaction or if it's an irreversible reaction. An arrow with 2 heads pointing in both directions is used to show us if a reaction is reversible. Okay, reversible reactions simply mean reactions that can go from reactant to product, and they can also go from the products back to the reactants. So you can see this compound, ammonium chloride, can react to form ammonia and hydrogen chloride. This product, okay, can also react to form this compound. And so we have an arrow pointing in both directions to indicate that. Same for water. We have water in its liquid form reacting to form gaseous water or steam. This steam can also react to form the liquid water. And so the arrow points in both directions. But you can see this third reaction here, sodium reacting with iron chloride to give us sodium chloride and iron, is just one way, meaning that this products cannot react again to form these reactants. It's a one-way reaction. There are points to note in the writing of chemical equation. The formula of reactants and products are fixed, okay? So they cannot change. If sodium chloride is supposed to react with, say, water, sodium chloride reacting with water to give us sodium hydroxide and hydrogen chloride, is telling us that the formula of these reactants are fixed. It cannot change. This will always react with this to give us this. So, to balance an equation, what we need to do is to take into account the number of moles of reactants and products. And then the next thing we do is to do an atom count. Remember that we need to make sure that the number of atoms on the right-hand side will balance or be the same with the number of atoms on the left-hand side. So you don't want to have less atoms on the product side than on the reactants. So it's a way of making sure that the law of conservation of matter is achieved in any reaction. And so we do an atom count. For instance, if we do an atom count for this reaction here, we have one atom of sodium, one atom of chlorine, and we have 2 atoms of hydrogen and 1 atom of oxygen. Coming over to the products, we have 1 atom of sodium, 1 atom of oxygen, 1 atom of hydrogen. Then we have 1 atom of hydrogen here and 1 chlorine. So it's balanced. We have 2 here, have 1 and 1 plus 1. That's 2. So this equation is balanced. We always do an atom count to make sure that our equations are balanced at the end of every reaction or whenever we write chemical equations. Here ends our class. A quick summary. We talked about the laws of chemical combination, and we talked about the law of conservation of mass, law of constant composition or definite proportion, the law of multiple proportion, and then we looked at chemical equations and how to balance equations. Let's have a little test to help us remember what we did today. Which of the laws of chemical combination implies that the total mass of reactants is always equal to the total mass of products formed? A, law of multiple proportion. B, law of conservation of matter. C, law of definite proportion. If you picked A or C, you're wrong. Our answer is the law of conservation of matter. Remember that this law says that matter is neither created or destroyed. Rather, it can change from one form to another. With this, we have come to the end of our class. Thank you for staying with me.